Okay, let's dive into this. Welcome to the Explainer. Today we're looking at a pretty massive development in AI news that is fundamentally shifting how we evaluate machine learning algorithms. We are looking directly at a really fascinating new arXiv paper, specifically paper 2607.08789 by Akshay Balsubramanian. And what this paper does is introduce the concept of intrinsic time. It proves an exact information accounting identity that honestly just completely rewrites the rulebook on how we understand regret in adaptive, Bayesian, and multiplicative-weights updates. So if you're working with sequential decision systems, this is something you absolutely need to understand.
Here is our cognitive roadmap for today. We're going to move pretty swiftly from the theory straight into practical developer takeaways. We'll hit 1. The old regret problem. 2. A new exact identity. 3. What is intrinsic time? 4. Upgrading algorithm design. And finally, 5. Production monitoring next steps. Section 1. The old regret problem. So the crucial point is that evaluating sequential decision systems has historically been, well, incredibly frustrating for machine learning developers, right? If you've ever analyzed traditional regret bounds, you know the absolute pain of worst-case upper bounds that are just packed with slack. You're forced to rely on these loose approximations, making really heavy adversarial assumptions just to get some sort of theoretical guarantee. And it often feels clunky. It feels totally disconnected from how your model actually performs on real day-to-day data. But this new paper essentially invalidates those old methods. It introduces a clean, exact pathwise identity. We're literally shifting from loose guessing to a deterministic equality that is evaluated pathwise on your realized sequence of feedback. It's a real game changer.
Section 2. A new exact identity. The core breakthrough here is that regret in Bayesian and multiplicative-weights updates isn't just a loose, high-probability bound anymore. You can actually think of it like a perfectly balanced accounting ledger. On each round, the learner's excess loss relative to any comparator splits exactly into two deterministic components. Component 1 is an immediate payment for the uncertainty exposed by that round, and Component 2 is a reduction in the information distance between the learner's current weights and the comparator. When you add those two together, boom, you get your exact excess loss. And this holds pathwise for every single realized sequence of feedback. No slack, no guessing.
And what's wild is the sheer scope of this breakthrough. This exact pathwise account doesn't change based on your specific update rule or your prior structure. It doesn't matter if you're using the hedge algorithm, optimistic inside information variance, continuous priors, or boosting. The same goes for online convex optimization, contextual bandits, or even modeling repeated games. The mathematical structure remains completely identical. One single, exact calculus covers all of these major algorithm families.
Section 3. What is intrinsic time? Now, what's really interesting about this slide is how this framework actually redefines time itself in the context of machine learning. Intrinsic time is basically a pathwise uncertainty clock. It's defined by that cumulative payment for uncertainty we were just talking about. And why does this matter so much? Because it's the realized intrinsic time trajectory, not some assumed worst-case regime that dictates your regret. Favorable conditions, things like stochastic environments, low-noise feedback, or highly predictable sequences, they manifest naturally as self-bounding properties of your realized sequence. You no longer have to assume a specific regime to get tight bounds. The trajectory just does all the heavy lifting for you.
Section 4. Upgrading algorithm design. So, if you're an engineer or a researcher building these sequential decision systems, how exactly does this change your day-to-day algorithm design and implementation? Let's take this pure math and pivot to some actionable developer best practices. Implementing this exact identity takes some really careful handling of your weight distributions. First off, when you're using multiplicative updates, your weights can easily underflow to machine epsilon. So, step 1, you absolutely must apply log space arithmetic. Track the log of your weights and compute the divergence using the log domain KL formula. Doing this completely prevents gradient explosion or silent NAND propagation during that uncertainty payment step. Second, for empirical validation, run your algorithm and record 3 distinct arrays per round: the uncertainty payment, the information distance reduction, and the excess loss. Finally, you want to verify that the excess loss equals the sum of the other two within your floating point tolerance. Typically, you're looking at 1E7 for float 32 and 1E15 for float 64. If you start seeing systematic drift outside those tolerances, well, that tells you there's a mismatch between your update rule and the theoretical composition.
Let's move to Section 5 and see how this builds into production monitoring next steps. Out in the real world, in live production environments, intrinsic time becomes an incredibly powerful diagnostic tool. You can literally use it as a direct system health metric. If intrinsic time is stable or just growing slowly, great, your system is efficiently converting feedback into weight updates. But if you see a rapidly accelerating intrinsic time, that signals a really high uncertainty exposure. You can also use it as a dynamic exploration threshold. Instead of relying on those outdated, clunky, heuristic epsilon-greedy schedules, you now have a mathematically grounded trigger derived right from your realized feedback sequence. When the cumulative uncertainty payment exceeds a set bound, you can fire off data quality alerts to trigger an explicit exploration phase, or automatically switch to a more robust prior.
Now, a quick practical heads up for the developers tuning in. While the full mathematical derivation is freely available over an arXiv, there isn't a production-ready drop-in library for this framework just yet. But honestly, the good news is you can easily implement this accounting identity yourself right into your existing weight update routines. Standard numerical libraries like NumPy, PyTorch, or JAX handle the required tensor operations perfectly. Just remember to use those stable divergence calculations we discussed so you can avoid NANDs when your weights inevitably approach zero.
And that brings us to the ultimate question for anyone working with adaptive Bayesian updates. Are you ready to shift your evaluation pipeline from worst-case guessing to exact pathwise intrinsic time tracking? The math is there, the path is clear, and the performance insights are just profound. I highly encourage you to check out the arXiv repository for the full proofs and consider completely overhauling your own AI evaluation pipelines. Thanks for joining me for this explainer, and keep exploring.